This video is about light, also known as electromagnetic radiation, and how we find out the nature and conditions of various objects by taking the light and passing it through a spectrometer to make a spectrum. In the lecture outline, the first set of vocabulary terms is about the general properties of light, and the second set of terms is about the three types of spectra: the continuous spectrum, the emission light spectrum, and the absorption line spectrum. Before I get into the general properties of light, let's look at imaging, taking pictures, versus spectroscopy, analyzing the spectrum. At least 95% of the information astronomers receive is in the form of light. That's why Chapter 7 of the Astronomy Notes textbook is probably the most important chapter that you should study carefully. Astronomy is different from the other sciences in that it is almost solely an observational science, in that the usual classical sorts of experiments cannot be done. You can't put a star or asteroid on a balance scale to measure its mass. You can't submerge it in water to find its volume from how much water it displaces. You can't find out what it's made of by taking it apart and doing chemistry experiments on it. All you can do is look at it from a great distance away. We do get a small fraction of information from meteorite rock chunks that fall to the Earth's surface, from space probes we send to the planets, asteroids and comets, and from superenergetic particles traveling great distances at nearly the speed of light called cosmic rays. But most of the information is in the form of light, so astronomers have had to devise ways to get as much information out of the light as possible. If you take a picture of something, you can find out such things as the brightness of an object, its shape, and its relative position. Object X is to the right of object Y, etc. Stars in a cluster can have different brightnesses. Some are bigger than others, and their colors may be different from each other. Images taken with different filters can be combined to give a nearly true color picture of the object, like the Hubble Space Telescope did for this picture of the central pillars in M16, the Eagle Nebula. But, by far, more information is decoded when the light is spread out into the individual colors that make it up to create a spectrum. A careful analysis of the spectrum can tell you about an object's temperature, speed, and direction of travel, chemical composition, gas density, surface gravity, structure, and more. Most of the things I'll describe in the course were found from spectroscopy, which is the study of an object by analyzing its spectrum. So what is light? Since it plays such a central role in astronomy, we'd better understand what it is and how the information is encoded in it. As noted in the first vocabulary term, light is electromagnetic radiation, which is made of fluctuating electric and magnetic fields that oscillate perpendicular to each other and perpendicular to the direction that the wave is moving. The definition of the first vocabulary term gives you the order of the forms of light from the lowest energy, radio, to the highest energy, gamma rays, which is from right to left on the picture here. If you go in the order of increasing wavelength, which is the distance between the crests or troughs of the wave, that is from left to right, with the shortest wavelengths being gamma rays, next is X-rays, then ultraviolet, then the tiny sliver our eyes can see is the visible or optical band, then the infrared, and finally the longest wavelengths being radio waves. The two links take you to good videos about the forms of light we cannot see with our eyes. Next in the lecture outline are three basic properties of light. The first is that it can travel through empty space, which is different than other waves like water waves or sound waves that require some material to travel through. That's great about light because we can get messages across vast empty reaches of space. And there's a lot of empty space in our universe. The speed of all forms of electromagnetic radiation is the same in empty space, about 300,000 kilometers per second, or 7.5 times around the Earth in 1 second. The forms of light have the same speed in empty space, but different wavelengths. which I already mentioned is the distance between the crests or troughs of the wave. Often the Greek letter lambda is used as shorthand for wavelength. Rainbows show that white light is actually made of many different wavelengths which correspond to the various colors. The rest of this slide is just vocabulary terms. Frequency is the number of wave crests that pass by you every second. Since all forms of light travel at the same speed in empty space, the frequency and wavelength are the inverse of each other. That means a low frequency or small frequency is a long wavelength, and a high or large frequency is a short, small wavelength. The animation shows a 3 Hz wave at top and a 1 Hz wave at bottom. The 3 Hz wave's wavelength is 1/3 as long as the 1 Hz wave at bottom. The next picture describes the wavelength, frequency, and energy of the various colors. Bluer light has a shorter wavelength and higher frequency, which means higher energy, than redder light, which has a longer wavelength and lower frequency and energy. Light can also act like a particle, a photon. Whether you see light acting as a wave or as a photon depends on how you observe it. Light can behave as both a wave and a photon at the same time. Digital cameras and your phone's camera use that fact. The energy of the light wave or photon depends on the frequency. The more of those wave crests pass by you every second, the more energy there is. The intensity is the number of waves per second, or the number of photons per second reaching you. It is not the energy of the wave or photon. A bright light is more intense than a dim light, but may not be more energetic. For example, an ultra-bright, intense infrared lamp emitting trillions of infrared photons every second won't be detected by an ordinary digital camera. But that camera will be able to detect something putting out just a few visible light photons. The last vocabulary term is temperature, which is a measure of the random motion energy of the particles, how much they're jiggling about in an object. At the bottom is a summary of the 3 temperature scales you'll come across in science.